In this video, we're going to start our very brief overview of organometallic compounds. So there isn't one particular chapter that covers these in your textbook, so we'll be pulling from a few different places. But these are very, very important in terms of synthesis because several of these organometallic compounds can make carbon-carbon bonds. So after a brief look at some general information, we're going to talk about some main group metals as this applies to the preparation of alcohols, and the transition metals we will save for another time. What is an organometallic compound? Well, it's something that has a carbon and it has a metal. But more specifically, it has a carbon connected to a metal. So we might have, for example, methyl lithium, where we have a methyl group and that carbon is connected to lithium. This is one that we saw last semester. If we have an alkyne anion with sodium as the counter ion, well, technically that is an organometallic compound. In contrast, if we have sodium methoxide, well, this contains a carbon and it contains a metal, but the metal is bonded to the oxygen, not to the carbon, so this is not considered an organometallic compound. Now, to name organometallics, in some cases it could be named as an alkyl metal. So this first example, this is methyl lithium. 2 L's because one is for the methyl and one is for the lithium. This as a substituent is a phenyl group, so this is phenyl lithium. For other types of compounds, we might need to name it as an alkyl metal anion. So here we're going to name our alkyl metal and then state what the anion is. So this is methyl magnesium bromide. So methyl magnesium is a single word and then a space and then bromide. So relatively straightforward in terms of naming. I just want to make sure that you've got the basics so that we can easily refer to an organometallic compound either by structure or by name. In the past, when we've talked about covalent bonds versus ionic bonds, we focus on covalent bonds between a nonmetal and a nonmetal, and here the atoms are sharing electrons. With ionic bonds, this is where we typically have a metal plus a nonmetal, and the bond is created because of electrostatic attraction. So a positive is attracted to a negative. Well, it's actually more complex when we're talking about bonding in organometallic compounds. Some of them are very much covalent with ionic character, and some of them are almost essentially ionic. And a lot of them are somewhere in between. So we could consider the difference in electronegativity. So carbon is 2.5, sodium and potassium 0.9, 0.8. Here there is a really big difference. And so a carbon-sodium bond or carbon-potassium is going to be highly ionic. With lithium, magnesium, now we're looking somewhere between covalent and ionic. So we can think of it as being slightly covalent, but very, 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 very polar. All right, so different from what we've talked about before, there really is kind of a whole spectrum of bonding characteristics. So given that there really is kind of a spectrum of bonding, then how are we supposed to write organometallic compounds? If we're thinking about methyl lithium, well, this is where it's got some covalent character, some ionic character, as we're talking about a bond between carbon and lithium. So commonly, we will see it written as if it is a covalent bond, or we might see it written as an ionic bond. The important thing is to think about how it reacts. And so it reacts like a carbon nucleophile, and so it can be helpful to write it this way because this is the way it reacts. But it is common to have it written this way. So if it is written with a covalent bond, then you just really have to consider the fact that this has a very big partial minus and a very big partial plus. And finally, with methyl magnesium bromide, this is another one that has some covalent, some ionic character. So this is another one that is very, very polar. It's most commonly written like this. So the magnesium has a plus charge and the bromine has a negative charge. So this might be the more accurate way to write it, but it's okay if we think of it like this. Ideally, we want to write it based on the bond, whether it's primarily ionic or primarily covalent. But in terms of a reaction, then you need to think of it the way that it reacts, which means we want to think of it as a nucleophilic carbon. And in our next video, we're going to start to look at the importance of these nucleophilic carbons. Probably the most important organometallic compound of magnesium would be an alkyl magnesium halide, better known as a Grignard reagent. So these can be made by treating an alkyl halide with magnesium metal. And then once you have the Grignard reagent, what kinds of reactions can that undergo? Now, what works for the Grignard? R groups could be methyl, it could be primary, secondary, tertiary, it could be vinyl, it could be aryl. So a lot of flexibility. When it comes to the halogen, iodines are much more reactive, more so than bromides, more so than chloride, which is much, much more reactive than fluoride. So fluorides are not used. Just in case you're interested, the mechanism involves electron transfer, where magnesium transfers an electron, reducing the, in this case, methyl bromide, giving us this radical anion. And then we have homolytic bond cleavage to give a radical and the anion. And then this radical and the radical cation will combine, leading to the Grignard reagent. So for the preparation of Grignard reagents, you can start out with an alkyl halide or a vinyl halide or an aryl halide. So in our first example, we have bromobenzene, and this can be treated with magnesium metal in a dry solvent such as diethyl ether. So this gives us phenyl magnesium bromide, which can also be called the phenyl Grignard reagent. If we started out with something like ethyl bromide, this could also be treated with magnesium in diethyl ether to give us ethyl magnesium bromide. Here we had just a couple of examples of how to prepare a Grignard reagent, but what we really care about is what happens next. Now, once we have generated a Grignard reagent, it is possible for this to react as a base. Very, very strong base. So here we have a terminal alkyne, and so the methyl can act as the base, grab off this proton, put these electrons onto the carbon, giving us, plus we have methane, plus we would have magnesium and bromide as the counter ion to this alkyne anion. So the first example would be a deliberate use of the Grignard as a base, but in some cases it might not be what we desire to have the Grignard act as a base. So we have to be really careful, because if we have a compound that has an acidic hydrogen, then this can act as a base, grab off that acidic proton, and we will make methane. So we've just quenched our Grignard, giving us methoxide. So this would be the most difficult way to make ethoxide, right? So this is not what we want to do. Another possibility is that if we have a little bit of water present, well, the Grignard can grab off that proton, we have methane, and we make hydroxide. Again, a very inefficient way to make hydroxide. So in some cases, reaction as a base might be your desired outcome, but more commonly, this is an accident. So when working with a Grignard, you have to make sure you're using the correct solvent, so no acidic hydrogens. You also have to make sure you have the right quality of solvent so that it is completely anhydrous and you don't have any water present. So we may have some desired or unintentional reactions of a Grignard as a base. In our next video, we're going to see what happens when a Grignard acts as a nucleophile. In our last video, we saw that a Grignard reagent can react as a base, but now we're going to take a look at what happens when a Grignard can interact with an electrophile. Keep in mind, even though we write a Grignard as if there is a covalent bond between the R group and the magnesium, we still want to think of it as if it looks like this because it acts as a source of a nucleophilic carbon. So this nucleophile can share its electrons with an electrophile, and in this case this would push the electrons that used to be shared between the carbon and oxygen. It pushes them onto an oxygen as another lone pair, giving us the alkoxide, which would exist as the magnesium bromide salt. Finally, when the reaction is worked up with aqueous acid, then the alkoxide can grab off a proton, giving us the alcohol, where two groups are what was originally present on the ketone or aldehyde, and one group is what was originally the Grignard reagent. So here we have a couple of examples. So here we have the phenyl Grignard, and this can react with acetaldehyde. So if these electrons are shared with the carbonyl carbon, pushing these electrons up here, and I am just going to include this. So step 1, these are mixed together, and then step 2, aqueous acid workup. So what we would be looking at is this comes from the Grignard, and then that carbon would be connected to what was the carbonyl carbon is now an alcohol, and this is our final product. Another example, we could have the methyl Grignard and react that with benzaldehyde, and in this case, here's our Grignard sharing its electrons here. Once again, think about mixing them together and then an aqueous acid workup. And what that gives us is this product. So notice this is the same as this, except that in the first example, the benzene is what came from the Grignard, whereas in the second example, it's the methyl group that came from the Grignard. So there is a lot of flexibility in terms of preparing Grignards and reacting Grignards with carbonyl-containing compounds. Also keep this in mind, if we're looking at a particular target, this often means that there are multiple ways that this can be prepared via a Grignard reaction. Here let's take a look at some more reactions of a Grignard reagent as a nucleophile. So in our first example, we are using formaldehyde, and if this is our Grignard, this can share its electrons here, push these electrons up onto the oxygen, which would give us the alkoxide intermediate, and then aqueous acid workup would give us this as our product. So this comes from the Grignard, and this comes from the aldehyde. Notice when we are starting with formaldehyde, what we make is a primary alcohol. In our second example, we have the same Grignard, but now we are reacting it with an aldehyde, in this case acetaldehyde. So our Grignard can share its electrons, push these electrons up onto the oxygen, giving us the alkoxide intermediate, and then aqueous acid workup will give us this product, where this piece comes from the Grignard and this piece comes from the aldehyde. And now, when we started with a regular aldehyde rather than formaldehyde, we make a secondary alcohol. And the third example, same Grignard, now we are reacting it with a ketone, push these electrons up onto the oxygen, forming the alkoxide intermediate. With aqueous acid workup, we will get this product. So this piece comes from the Grignard and this comes from the ketone. Notice, because we started with a ketone, we end up with a tertiary alcohol. So a Grignard reaction with an aldehyde or ketone gives us access to primary, secondary, and tertiary alcohols. All right, so let's pull it all together. If we are starting out with an alkyl bromide, an aryl bromide, we can treat that with magnesium in the presence of an inert dry solvent to generate a Grignard reagent. And then the Grignard reagent can react with formaldehyde to give this alcohol. It can react with other aldehydes to give a secondary alcohol. It can react with a ketone to give a tertiary alcohol. Grignard reagents can also react with different types of species, so more than aldehydes and ketones, but these we're going to wait until later this semester. So for now, even if we limit our discussion to aldehydes and ketones, this still gives us access to primary, secondary, and tertiary alcohols.